Anchoring points on roof should be bonded to the grounding electrode system. According to National Electrical Code Section 250.104a, all metallic objects that are likely to become energized or carry induced currents must be connected to the grounding system. Anchoring points fall under this category. They are made of steel and exposed to the elements, which can induce currents. Regarding whether anchoring points act as air terminals, structures with a roof pitch of 4.12 or greater require air terminals, as stated in National Electrical Code Section 810.11, to protect against lightning strikes. However, anchoring points aren't specifically designed as air terminals. They might not meet all of the requirements for air terminals in National Electrical Code Section 810.11. Firstly, you should bond the anchoring points to the grounding electrode system. This ensures they are connected to the electrical system, and any induced currents will be safely dissipated. Secondly, consider installing additional air terminals on the roof. If the anchoring points aren't sufficient as air terminals, install dedicated air terminals that meet the requirements of National Electrical Code Section 810.11. Thirdly, use rubber boots when the anchors aren't in use. This helps protect against corrosion and accidental electrical contact. The bonding conductor size should be in accordance with National Electrical Code Section 250.104c. The bonding point should be located as close as possible to the anchoring point. All connections should be made securely and weatherproofed. Regular inspections should be performed to ensure the bonding system remains intact and functional. By following these recommendations, the anchoring points can be safely installed. This will provide a secure means of tying off while working on the roof, and also minimize the risk of lightning strikes. When dealing with grounding and bonding, understanding the relevant National Electrical Code articles is critical. National Electrical Code Section 250.104 is particularly important. It mandates the bonding of metal parts that could become energized. This includes parts that might carry induced currents. These currents can arise from various sources. Atmospheric electricity and nearby electrical systems are included. For grounding electrode systems, one should reference National Electrical Code Article 250.50 through 250.70. These sections describe the requirements for creating an effective grounding path. This path is essential for safely conducting fault currents. When installing air terminals, National Electrical Code Section 810.11 provides guidelines. This section specifies the height, spacing, and materials for air terminals. The goal is to create a zone of protection. This zone minimizes the risk of lightning strikes. Ensure that all bonding connections are mechanically sound and corrosion resistant. Use appropriate connectors and methods approved for the materials being joined. Regular inspections are critical. They help identify any degradation or loose connections over time. Correct any issues promptly to maintain the integrity of the grounding and bonding system. The size of the bonding conductor is determined by the equipment grounding conductor size. Consult National Electrical Code Table 250.102 code for proper sizing. This table ensures the conductor can safely handle potential fault currents. Consider using exothermic welding for critical connections. This method creates a permanent low-resistance bond. It eliminates the risk of loosening over time. When installing ground rods, ensure they are driven deep enough to reach moist soil. This improves their effectiveness as grounding electrodes. Spacing multiple ground rods at least 6 feet apart can also enhance their performance. In areas with high soil resistivity, consider using ground-enhancing materials. These materials improve the contact between the ground rod and the earth. This reduces the overall grounding resistance. Always consult with a qualified electrical engineer or inspector. Ensure compliance with all applicable codes and standards. This is essential for safety and proper system function. Furthermore, it is important to understand the principles of electromagnetic induction. Metallic objects exposed to electromagnetic fields can develop induced currents. This is because the changing magnetic field creates a voltage in the metal. This voltage can then drive a current. The magnitude of the induced current depends on several factors. These include the strength of the magnetic field, the size and shape of the metallic object, and the conductivity of the metal. In the case of roof anchoring points, they are exposed to atmospheric electromagnetic fields. They are also near electrical wiring within the building. These sources can induce currents in the anchoring points. Bonding the anchoring points to the grounding electrode system provides a path for these currents to flow safely to ground. This prevents the buildup of voltage on the anchoring points. This reduces the risk of electric shock to anyone who might come into contact with them. Lightning protection systems work by providing a low impedance path for lightning current to flow to ground. Air terminals are designed to intercept lightning strikes. They safely conduct the current down to the grounding system. If the roof anchoring points are not specifically designed as air terminals, they may not provide adequate protection against lightning strikes. The design and installation of lightning protection systems should adhere to National Electrical Code Section 810. This section provides detailed requirements for air terminals, conductors, and grounding electrodes. A properly designed and installed lightning protection system can significantly reduce the risk of damage to a building and injury to its occupants. Remember that a grounding system is not a substitute for overcurrent protection devices such as circuit breakers and fuses. Overcurrent protection devices protect against overload and short-circuit conditions. The grounding system provides a path for fault currents to flow to ground. This allows the overcurrent protection device to trip and energize the circuit. Both grounding and overcurrent protection are necessary to ensure electrical safety. Regular maintenance of the grounding system is essential to ensure its continued effectiveness. This includes inspecting connections for corrosion, verifying the integrity of grounding conductors, and testing the resistance to ground. Any problems should be corrected promptly to maintain the safety of the electrical system. The grounding electrode system typically consists of one or more grounding electrodes that are connected together to form a low impedance path to earth. Common types of grounding electrodes include ground rods, ground plates, and underground metallic water pipes. The grounding electrode system should be sized according to National Electrical Code requirements based on the size of the service entrance conductors. The grounding electrode conductor connects the grounding electrode system to the service equipment. The size of the grounding electrode conductor is determined by National Electrical Code Table 250.66. The equipment grounding conductor provides a path for fault currents to flow back to the source. This allows the overcurrent protection device to trip and de-energize the circuit. The equipment grounding conductor should be sized according to National Electrical Code Table 250.122. In addition to bonding the roof anchoring points to the grounding electrode system, it is also important to bond any other metallic objects on the roof that could become energized. This includes metal flashing, gutters, and downspouts. Bonding these objects together creates an equipotential plane. This reduces the risk of voltage differences between different metallic objects. This further reduces the risk of electric shock. When working on roofs, it is important to follow all applicable safety regulations. This includes using appropriate fall protection equipment such as harnesses and lifelines. Workers should also be trained in safe work practices. The use of rubber boots over the anchoring points when not in use is a good practice to prevent corrosion and accidental contact. The rubber boot should be made of a material that is resistant to ultraviolet light and weather. They should also be properly sized to fit snugly over the anchoring points. The location of the bonding point should be as close as possible to the anchoring point to minimize the impedance of the bonding conductor. This ensures that fault currents can flow quickly and easily to ground. The bonding connection should be made using a listed connector that is suitable for the materials being joined. The connector should be installed according to the manufacturer's instructions. All connections should be made securely and weatherproof to prevent corrosion. Regular inspections should be performed to ensure that the bonding system remains intact and functional. This includes checking for loose connections, corrosion, and damage to the bonding conductors. Any problems should be corrected promptly to maintain the safety of the electrical system. In summary, bonding roof anchoring points to the grounding electrode system is an important safety measure. It helps to prevent electric shock and minimize the risk of lightning strikes. By following the recommendations outlined above, you can ensure that the anchoring points are safely installed and provide a secure means of tying off while working on the roof. Remember to always consult with a qualified electrical professional for any electrical work. They can ensure that the installation meets all applicable codes and standards. Also, be sure to stay up to date on the latest revisions to the National Electrical Code. The National Electrical Code is updated every 3 years. This ensures that electrical installations are performed safely and effectively. The purpose of grounding and bonding is to create a low impedance path for fault currents to flow back to the source. This allows the overcurrent protection device to trip and to energize the circuit. Grounding also helps to stabilize voltage to earth. This reduces electrical noise. Bonding connects metallic objects together to create an equipotential plane. This reduces the risk of voltage differences between different metallic objects. There are several different types of grounding systems. These include grounded systems and impedance grounded systems. Each type of grounding system has its own advantages and disadvantages. The type of grounding system used in a particular application depends on the specific requirements of the application. The grounding electrode system should be installed in accordance with National Electrical Code Article 250. The grounding electrode system should be sized according to National Electrical Code Table 250.66. The grounding electrode conductor should be sized according to National Electrical Code Table 250.102 cone. The equipment grounding conductor should be sized according to National Electrical Code Table 250.122. Bonding jumpers should be used to connect metallic objects together. Bonding jumpers should be sized according to National Electrical Code Table 250.102 cone. All connections should be made securely and weatherproofed. Regular inspections should be performed to ensure that the grounding and bonding system remains intact and functional. Any problems should be corrected promptly. The grounding electrode system should have a resistance to ground of 25 ohms or less. If the resistance to ground is greater than 25 ohms, additional grounding electrodes should be installed. The grounding electrode system should be tested annually. The test should be performed by a qualified electrician. The results of the test should be documented. The documentation should be kept on file. Lightning protection systems are designed to protect buildings and other structures from lightning strikes. Lightning protection systems consist of air terminals, down conductors, and grounding electrodes. Air terminals are installed on the roof of the building. Down conductors connect the air terminals to the grounding electrodes. Grounding electrodes are installed in the ground. When lightning strikes a building with a lightning protection system, the lightning current flows through the air terminals, down conductors, and grounding electrodes to ground. This protects the building from damage. Lightning protection systems should be installed in accordance with National Electrical Code Article 810. Lightning protection systems should be inspected annually. The inspection should be performed by a qualified lightning protection contractor. The results of the inspection should be documented. The documentation should be kept on file. Surge protective devices, or SPDs, are designed to protect electrical equipment from voltage surges. Voltage surges can be caused by lightning strikes, power outages, and other events. SPD are installed at the service entrance of the building. They divert voltage surges to ground. This protects the electrical equipment from damage. SPD should be installed in accordance with National Electrical Code Article 285. SPD should be inspected annually. The inspection should be performed by a qualified electrician. The results of the inspection should be documented. The documentation should be kept on file. Ensure that all electrical work is performed by a qualified electrician. Electrical work can be dangerous. Improperly installed electrical wiring can cause fires, electric shock, and other hazards. It is important to follow all applicable codes and standards when performing electrical work. Always disconnect power before working on electrical equipment. Use appropriate safety equipment, such as rubber gloves and safety glasses. If you are not qualified to perform electrical work, hire a qualified electrician. Remember safety first.